Hello everyone. My name is Kehan. I am currently a PhD student at University of Notre Dame, and today I'm gonna present a work that is in collaboration internally in Notre Dame via Zhang's lab, which is my lab, and also with Professor Nitesh Chawla and all of West. So in this work, we are presenting ChemOrch, that is an open scalable pipeline that turns chemistry tool into executable, verifiable, and controlled instruction answer data for large language model. The goal is to reliably evaluate and improve chemistry capable models in way that directly serve for synthesis and discovery. So why this aligns with the CCAS goals? Because we presented data-driven synthesis that we use machine learning and domain tools to accelerate discoveries and enable new reactions. And also, this has been completely open sourced to a subtool library, so which enables the other design to be shared and extended. And lastly, this is a disciplinary training that it is a joint collaboration from the CS and chemistry workflow that cultivates the data chemist. So basically, here's the problem as we identified the gap in chemistry instruction data set. So as we have known that the current large language model has excelled in a lot of tasks, but the story is not the same in the chemistry domain because the large language model lacks reliable domain-grounded chemistry instructions and verifiable answers. And for existing data sets, most of them are from the patent data, and they have the limited coverage and they have the weak executability. And the instruction data sets are sometimes hard to control the difficulty in which the LM cannot understand and proceed correctly. So in this case, the community is called for the need that we need the diverse, executable, and controllable instruction that reflect the real chemist task. So given that, we are proposing to leverage in the chemistry tool in two different ways. So basically, we are trying to build a two-stage pipeline that we want to teach teach the large language model how to use tools, and we are also using the tools that has done by the community to generate a various data sets in which later can be a feedback to the large language model to improve its ability in the domain of chemistry. So basically, it's a two-stage pipeline. And for the first stage, we are proposing a task-controlled instruction generation that we have collected a bunch of chemistry tools like RDKits or PubChem APIs, and we utilize the tools plus some constraints and some metadata to generate instruction data sets from different difficulty feedbacks. And for the stage two, we are using the tool where we call that tool aware response construction that we have decomposed each each different task. And for those, we'll select some subtasks and using the subtask, we can generate code. And with the code, we can execute with the self-repair or sufficient checks that whether these answers are valid or not. And using that, we can produce verifiable, reproducible output that we can later use that to generate the response for the instruction tuning of the large language model. So concretely, think this is the pipeline of the overall process I have just described. So basically, let me just walk you guys through like a detailed pipeline. We begin by feeding the official documentation of RDKit and PubChem into the large language model. such as GPT-4, as you can see here. And then we'll apply a few-shot learning approach to guide the extraction of function level operations. These operations, which represent the atomic unit of the functionality, are identified based on their relevance to common chemistry tasks. The large language model is then prompted to synthesize this operation into callable Python code, each encapsulated as a subtools. And every subtool is constructed following a schema consisting of five components, as demonstrated here. So the semi-automated process significantly accelerate tools decomposition while maintaining structural consistency. And to ensure the correctness and usability, we subsequently perform a manual review of all generated subtools. That is a human annotation. And so basically, with that, we have collected 74 subtools in total, and 57 from RDKits, and 17 from the PubChem. And we annotate this with atomic callable functions with description, keyword arguments return minimal examples, as we have demonstrated here. So basically, using that, we could construct a very comprehensive instruction tuning data sets to for the large language model. So when prompted with a new task, it can actually understand what kind of task it is, and inject the tool using ability to the large language model for it to generate executable code to generate to finish the task. So basically, here is the results of our generated data sets. And to assess the instruction data set diversity and coverage, we have adopted two quantitative metrics. The first is APS, that is the average pairwise sample similarity, and the remote click. That we use to capture the diversity and quality of the generated data sets. And as shown in Table 1, the dataset generated by our proposed method achieved significantly lower APS and higher remote click compared to the ChemLLM bench. That is our baseline. And that suggests that our method often improved diversity and better structural spread in generation. And you can see in the Fig 3, that is the word distribution from the left to right. That reveals our generated data sets has a higher diversity. And Fig 4 shows the distribution of the answer generation. So basically, as you can see, the majority of the tokens are spreaded into the tool selection. That indicates that our instruction data sets contains a lot of instructions on how to instruct how the model to use tools. And here is the key results. Actually, upon testing the large language model in our generated data sets, we reveal the weaknesses of the current large language model. That with our data set, it has a very low performance in most of the data sets. The result actually shows that most models perform poorly on this task, and that needs further improvements. So with that, we take the last step. That is, we fine-tune the large language model in our generated task. We use the Llama 3.1 8B instruction model and the Qwen 2.57B instruction models to do the supervised fine-tuning, which is we want to inject the knowledge of our instruction data set into the large language model. And as we can show in Fig 3, the probability prediction accuracy increased by around 35% for the Llama 3 models, and indicating that a strong performance of our data sets for the model improvements. And also for the model caption, we see some moderate improvements as well for both models. And for the tool usage ability, we can see that after the fine-tuning of our data set into both models, we see improved tool using ability that indicates that the large language model fine-tuned by those data sets can actually execute tools and generate some reasonable code to get the final results. And more detailed results can be found in our paper. We have open sourced the code and the PDF files, so that if you have tools that can also be used to generate the results, we're happy to contact. So basically, in summary, we build a ChemOrch that is a two-stage pipeline, and the core value is to produce the executable, verifiable results. And also we show that our work can improve the large language model into those tasks. And our future plan is to build a automatic system that integrate more tools and probably automate the whole synthesis generation to experimental execution pipeline. Yeah. That's all for the presentations. We're happy for any collaborations or questions.
All right. Thanks, Kehan. We have time for one quick one. Ramil?
Thanks. Are you using any MCP here to managing tools execution and comments on tools and multi-agents?
No, no, those are our next steps. So for the tool usage, we manually labeled a lot of the tool instructions, and based on that, we kind of fine-tune a third models to judge on how the tool usage or how the tool selection is correct or not. But I agree that we should use the multi-agent framework in the future to have a more precise tool execution determination.